So yeah, good morning, everyone. My name is Karlheinz Muth. I'm Senior Principal System Architect and member of the Broadcom Silicon Photonics founding team. And I will talk about anticipated paradigm change in high-speed interface technology today. You might have seen data like this that we have zettabytes of cloud data movement, and in these systems, which are mesh of optical fibers between servers and the data center core, there are 1 million or more optical interconnects. And there's also a huge growth in annual intra-data center traffic. So most of the traffic is actually within the data center compared to external traffic. Also, the optical interconnects, they dominate the cost of these systems because you have these optical transceivers in the front panel, which is usually 32 up to 64 optical transceivers compared to a single switch. So the cost of optics is also increasing with increasing speeds and increasing throughput in these systems. What we anticipate is a change of how these systems are built, the transformation in these optical systems. So from traditionally going optical transceivers and optical components packaged and somehow assembled together in a non-integrated version, we see a transition from silicon germanium to CMOS, from optical transceivers to switches with directly co-packaged optical IOs and also later optical interfaces directly integrated on and discrete optical components migrating to silicon photonics. So at the end that we have integrated optical systems. Now, how does it work? So co-packaging is an integration of multiple dies on a common substrate. This is already done today in high volume with high bandwidth memory, and is expected to grow also year over year. Co-packaged optics is very similar. It's the integration of optical engines on the same package substrate that an switch or other communication ASIC to shorten the electrical link and to save power and cost. If we look at I/O efficiency, starting from which is the speed divided by density per picojoule per bit. So meaning the denser, the lower power, the higher the speed. So FPP's front plane pluggable modules and onboard optics have a fairly low efficiency. Then there is a proposal for near package optics, which is closer to the actual communication ASIC. But what we are trying to do is integrating this higher and higher to achieve very high density and saving cost and power at the same time by going to CMOS silicon photonics and also using multiple wavelengths. This is not possible with copper to use pretty much frequency division multiplex on copper channels is only possible with light, and this is what we anticipate as the future of these optical interconnects. What are the key building blocks to achieve this? So you need, of course, the switch silicon or a GPU, TPU processors with some high-speed I/O. Then you need mixed signal ICs to prepare to process the signal to be to be sent to the optics and optical devices and the fabs. And very important is also advanced packaging and tests, so chip-on-chip technologies, for example, TSVs, and also optical packaging and fiber routing. And silicon photonics finally enables all that technology, because we can do very high density photonic integrated circuits, modulators, photodetectors, and other components are possible to be integrated in silicon photonics. So this whole set of building blocks will drive a system solution for this co-packaging market with optics. So this means we can optimize the system along many vectors. If we combine the technologies with advanced packaging, instead of, for example, having monolithic optics. So that gives us the freedom to optimize each component by itself and then integrate it with advanced packaging. Important is also co-simulation, optical co-simulation, which is still compared to the quality of simulations for electrical links, still is in its infancy, also regarding the system level. And tool suppliers and so forth are working on this, but it's not at the same level, in my opinion. And so this co-design also for signal integrity, power integrity, mechanical and thermal constraints to achieve at a system level solution. So compared to these multiple transceivers, they will migrate to an integrated system where you have a high-speed communication ASIC in the center of a package, and then co-packaged optical engines together with this chip. How does that evolve now with the platform in volume and bandwidth? So if you look at traditional front panel transceivers, they contain a signal processing engine to handle the electrical channel between the core silicon and the optics. And this becomes more and more tricky the higher the speeds will become. Going to 100 gigabit and 200 gigabit per second per channel, these electrical channels have much more penalty than the optical channel, for example. So if you look at the scaling, the density, cost, and power consumption, this will go up as you try to scale it with these transceiver modules. So the proposal is then to just eliminate this electrical channel more or less, and make it a very short on-package channel that allows to eliminate the DSP in the optics and use the DSP in the core silicon in switch ASICs or GPUs or whatever this core communication ASIC does, and have just a simple electro-optical conversion in an optical engine close by. To make this whole co-packaging system reliable, remove the laser and have a remote laser source just to supply the photonics engine with optical power. And this is scalable. So this scales with channels and bandwidth, also with cost and power consumption and density. Now, how do we do that? Because we want to keep the same functionality what we had with these individual transceiver modules. So what's in a typical transceiver module? As I briefly mentioned before, there is a DSP, a digital signal processor, which handles on one side the optics, on the other side the electrical channel. Then you have a transmit section with a transmitter IC and a silicon photonics transmitter, a laser integrated, and on the receive side a similar structure with a transimpedance amplifier and the receive optics. And besides that, there are also DC-DC converters in such a module, and there's a control circuit, a microcontroller, and memory and other control units to control this, to get this module controlled by the system. Now we simply take these modules and build virtual transceivers. So if we disassemble, then we just take away the power supply and the control and the laser, remove that from the system and concentrate it at a control module, either on a front panel pluggable or on onboard form factors, and we keep the existing control concept. Then we can remove the digital signal processor from the system and finally combine many channels in a single optical engine, like it is shown here on the top right. And for the power source, for the laser and control for the optical power supply, we still use a front panel pluggable module because from a point of reliability, the lasers are not as reliable as silicon or silicon photonics, and they might have to be exchanged during the lifetime of a system. We call this remote laser source or remote laser module. Here's a block diagram how this looks like. It's very simple actually. So from the left side, the system typically is managed the way that there is a system CPU processing unit, which has two main controlling paths. One is the actual switch, the core ASIC silicon, and on the other hand, there is a control section which manages these optical transceivers, which is an I2C bus, and the protocol is called CMIS. So this is a common management interface specification. So this defines how these modules are controlled. If we now go to the virtual transceiver, we simply redistribute the components in the system. So from the system side, there are still these two main paths, and we just co-package the optical engine and then have the laser and control section separate with either a standardized or proprietary protocol to control the optical engines. But from the system side, this still looks like a transceiver. That's why we call it virtual transceiver. Now, how does that look like in reality? So on the left side is a sketch how these systems can look like. On the right side is a sample of such a prototype system. This is a 25.6 terabit Ethernet switching ASIC, and in this system it's called half optics because half of the channels, 256 channels with 100 gigabit per second each, are still going through the front panel for copper interconnects, and half of the channels are run through these optical engines on the optical side. The package is still pretty small. It's smaller than 70 by 7 substrate size, and each engine has 32 terabit transmit receive full duplex, and is about 15 by 20 millimeters in size. And in this case, we are saving about 1 watt per channel compared to front pluggable modules. And these are here the cables where we feed the optical power in, and then we have transmit and receive. Then we can look at the whole demo system. This is the whole box. So on the right side is a sketch. On the left side is how this whole box looks like. So on the left side here are these cages for the copper interconnects, and here you can see the optical engine. So there's a fan-out cables. So for measurement purposes, Then on this side is the CPU. The whole thing here is a cooling system, cooling fans, and the fiber routing is below that blue plastic here. And on the top left side, on the bottom left side, are 4 laser modules, where one laser module is supporting one optical engine. This one laser module contains 8 lasers, and we have a 1-to-4 split, meaning one laser is supporting 4 optical channels, so that we get to 32 channels as a whole. Now let's look a little bit at the performance parameters. So on the left side is a sketch again. So we're using liquid cooling here, and I have to say this is not needed. Liquid cooling is not needed. So the actual box is really run with fans, but these fans are incredibly loud. And if you do testing in the lab, they'll throw you out if you keep running these fans all the time. That's why we use liquid cooling in that case, and that's a very good possibility for lab testing without having this noise pollution always around the testers. And this is these are eye diagrams of the transmitter at full rate and half rate. So we achieving TDQ numbers below 2 dB and optical extinction ratio above 4 dB at half rate. The whole system is a little better, but these are numbers which are much better than the optical standards at the interface would require. And on the receive side, we have the following test setup. So we are using a regular optical transceiver to show interoperability. Then we're using an optical amplifier for overload testing, an attenuator, and then a 1-to-8 optical switch so that we can test one island of an engine. So the one engine has 32 channels, but these 32 channels are segmented in blocks of 8. So in these blocks of 8, we call that an island. So we can test one island with this manual setup at a time. The whole thing is then also controlled via Ethernet and run automatically. This is the eye diagram we're testing the receiver with. So the TDQ is about 2 dB. So this is not quite the worst case. Transmitter you could get from a standards perspective, but it's I would say more typical, has also some nonlinearity. So this is not a perfect transmitter we are using to make this whole testing a little more real. And then here's the results we're getting for 8 channels. On the left side is the bit error rate. On the bottom side is the optical modulation amplitude in dBm. And this black line here is the limit. So we need to stay below this limit. And as you can see, we are well below this limit for the bit error rate pre-fact, meaning before forward error correction is applied. And so that black line down here, that dark line or dark blue is it, that is our simulation result. And so we are still missing about a dB of signal to noise ratio, where we found that we can improve especially on the SerDes receiver side, and also on the linearity of the TIA of the receiver here in this overload condition above 0 dBm. So the final design will eliminate that and move closer to the simulated value. You can also see that the variation in these channels is there, but it's not drastic. So this is also a very important item, that these channels are not too different from each other. This is just a the diagnostics. So the diagnostics are important for the testing. So these are eye diagrams we extract from the inside of the switch ASIC, of the main ASIC, and so we can plot eye diagrams in front of the analog digital high-speed analog digital converter, and also after the equalization here on the right side. So we see an open eye and a VR of 4.3 minus 8 in this case. One other important part is the bit error rate after applying forward error correction, and it works the way that you can have, and this is a Reed-Solomon code with an error capability of 15 errors per code word. This is this red line here. On the left side are these bins, meaning it counts errors, and it puts errors in there from a single error, 2, 3, 4, 5, 6, 7, and so forth errors per code word. And red is the area where errors occur, and green is the area where no errors occur. And you can see that we have quite the dynamic range here where the forward error correction works. So there is no hidden issue in this system regarding the correctability of errors. The whole plot is versus input power. I think it's a 13 dB dynamic range, and practically we have a dynamic range of around 8 dB. So this is also showing that these systems are compatible to common transceiver level systems and don't show any disadvantage in the performance. So overall, this concept gives us 30% total power savings of the total box compared to a transceiver solution. It's more like 50%, so half the power compared to transceivers. Here on the top right side is the next system that will be a 50 terabit system that we are working on. We expect a 50% improvement in density. So we can, for example, we can build this 50 terabit system in 1 RU in this small pizza box, and also a significantly lower cost per bit per second in these systems. And finally, there is some roadmap what we are planning to do. So we still we focus on hyperscale, very high density systems. We still will also build transceivers, but we are using these ingredients to co-package that with the Broadcom switches, 25.6 tera, 50 tera, and then the next generation would be 100 terabit. We're also going from 3.2 terabit per engine to 6.4 to 12.8. And this system is also suitable for compute platforms, as I mentioned before, like graphics or tensor processing units, which have a dense mesh for intercommunication and the need for very high density. So in summary, I'd say that future systems will require high density and lower power per bit. And we see a paradigm change from transceiver modules to chiplets, which can address this issue, basically coming from a module play, if you will, to a chip, an IC play in this market. And advanced packaging, 2D, 3D packaging, and heterogeneous optical integration will enable that. This will automatically lead to improved performance and cost, also improved reliability, because integration usually leads to higher reliability overall.